Bridge, position, shape, and architecture trade-offs. Transformers are powerful, but they are not simple. Every design decision, from how position is encoded to the dimensions of the layers, involves trade-offs. These trade-offs balance capacity, efficiency, stability, and generalization. Understanding them means understanding why transformers are built the way they are and what constraints shape their design. We'll explain why these architectural choices matter and how to think about the trade-offs that guide modern language model design. Let's start with a fundamental problem. Transformers have no inherent notion of position. Attention computes similarity between tokens and forms weighted sums, but this operation is permutation invariant. If you scramble the order of tokens in a sequence, attention produces the same output, just in a different order. For language, position matters enormously. The cat chased the dog and the dog chased the cat have different meanings, even though they contain the same words. The transformer must be told which token comes where. The solution is positional encoding, adding information about position to the token representations. This seemingly simple requirement has profound implications. How you encode position affects not just what the model can learn, but how efficiently it can generalize to sequences longer than those seen during training, how it handles relative versus absolute position, and how much capacity is consumed by position information rather than content. The original transformer used sinusoidal positional embeddings, which are fixed functions of position based on sine and cosine waves of different frequencies. These embeddings are added to the token embeddings before the first layer. The advantage is simplicity, no parameters to learn, and the functions generalize to any sequence length. The disadvantage is that position information is only injected at the input. Deeper layers must rely on this initial encoding, which can degrade over many layers. Additionally, sinusoidal embeddings encode absolute position. Token 5 is always token 5, which may not align with how language works.
In many cases, what matters is relative position. Is this word 2 positions before or 3 positions after? An alternative is learned positional embeddings, where position is represented by a learned vector for each position. This allows the model to adapt the position encoding to the data, but it limits the model to a maximum sequence length equal to the number of learned positions. If the model is trained on sequences of length 1000, it cannot directly handle sequences of length 2000. Extrapolation to longer sequences requires techniques like positional interpolation or changes to the encoding scheme. Some models have been fine-tuned to extend their context by interpolating between learned position embeddings, but the results are often imperfect. Longer contexts work, but with degraded quality. A more recent innovation is rotary positional embeddings, or ROPE. ROPE encodes position not by adding embeddings, but by rotating the query and key vectors in attention by an angle proportional to their positions. This rotation is applied at every layer, so position information is continually refreshed. The key advantage is that ROPE encodes relative position. The attention score between tokens depends on how far apart they are, not their absolute positions. This makes the model more flexible and improves extrapolation to longer sequences. The math is elegant. Rotation preserves distances while changing orientations in a way that naturally encodes offset. Why does ROPE work? Because rotation preserves vector norms while changing angles. When computing attention, we take the dot product of queries and keys. The dot product measures both alignment and magnitude. By rotating queries and keys, ROPE modulates their alignment based on position without changing magnitudes. Tokens that are close together have small relative rotations, so their dot products remain large.
Tokens that are far apart have large relative rotations, so their dot products decrease. This injects position information directly into the attention mechanism in a mathematically principled way.
Rope has become the dominant positional encoding scheme in modern transformers. Models like Llama, Palm, and many others use rope because it's effective, efficient, and generalizes well. Understanding rope requires understanding how attention computes similarity and how rotation affects that computation. The paired lecture will walk through the mathematics, how rotation matrices are constructed, why they encode relative position, and how they're applied efficiently in practice. Your task is to connect the formulas to the intuition. Position is encoded as rotation, and rotation modulates attention based on distance. Now let's turn to model shape, the dimensions of the layers. A transformer is characterized by several hyperparameters: the embedding dimension d, the number of layers L, the number of attention heads h, and the feed-forward dimension, typically 4 times d. These dimensions determine the model's capacity, which is its ability to represent complex functions, and its computational cost, which is the flops and memory required for training and inference. Why do we choose specific dimensions? The embedding dimension d determines the richness of token representations. Larger d means each token can be represented with more features, allowing the model to capture more nuances. A 4096-dimensional embedding can encode far more distinctions than a 512-dimensional one. However, larger d also means more parameters in every weight matrix, increasing memory and compute. Every attention projection, every feed-forward layer scales with d squared, or d times the feed-forward expansion. The costs compound quickly. The number of layers L determines the depth of processing. More layers allow more transformations of the representation, enabling the model to learn more complex functions. Each layer can refine the representation, adding nuance and abstraction. A 12-layer model might learn surface-level patterns, while a 48-layer model can learn deeply hierarchical structure. But more layers also mean more memory for activations and longer training times. There's also a point of diminishing returns. Beyond a certain depth, additional layers provide less benefit unless the width also increases. The number of attention heads, h, splits the embedding dimension into h independent attention computations. Each head learns to attend to different patterns. More heads provide more diversity, allowing the model to capture multiple types of relationships simultaneously. However, each head operates on a smaller subspace, d divided by h, which limits the expressiveness of any single head. The trade-off is between having many weak heads or few strong heads. Empirically, models typically use between 8 and 64 heads, depending on the embedding dimension. A common pattern is to keep the head dimension around 64 to 128, then scale the number of heads as the embedding dimension grows. The feed-forward dimension is usually set to 4 times the embedding dimension. Why 4? This is a heuristic that balances capacity and cost. The feed-forward layer expands the representation into a higher dimensional space, applies a nonlinearity, and projects back down. The expansion factor determines how much intermediate capacity the layer has. 4 is a common choice, but some models use 3, others use 5 or more. If gated feed-forward layers are used, the effective dimension is often reduced to maintain parameter parity. For instance, sweet glue uses a 2/3 expansion because gating effectively doubles the parameter count. Another shape consideration is the vocabulary size. Language models have vocabularies of 30,000 to 100,000 tokens. Larger vocabularies allow more precise tokenization,
reducing sequence lengths and improving representation of rare words. But larger vocabularies also mean more parameters in the embedding and output layers, which can dominate memory in small models. For a 100,000 token vocabulary with a 4096 dimensional embedding, the embedding matrix alone contains 400 million parameters. That's substantial, especially if the rest of the model has only a few billion parameters. Choosing vocabulary size involves balancing tokenization granularity against parameter overhead.
Some recent models tie the input embedding and output projection matrices to halve this cost. Why do these shape choices matter? Because they determine the model's scaling behavior. Larger models are generally more capable, but they scale in both capacity and cost. If we double the embedding dimension, we roughly quadruple the parameter count, because most parameters are in weight matrices proportional to d squared. If we double the number of layers, we double the parameter count and the compute per forward pass. Understanding these scaling relationships is essential for planning experiments and allocating resources. Researchers use scaling laws, empirical relationships between model size, data size, and performance to guide these decisions. The paired lecture will discuss how different models choose these dimensions and what patterns emerge across the field. You'll see that most modern models converge on similar shapes, guided by empirical results and hardware constraints. For example, many models use embedding dimensions of 4,000 to 8,000, depths of 20 to 60 layers, and 16 to 40 attention heads. These choices reflect a collective understanding of what works well, refined through years of experimentation. But the convergence also raises questions. Are we stuck in a local optimum? Could radically different shapes work better for different tasks? Not all models follow the same template. Some prioritize depth over width, using many narrow layers. The hypothesis is that depth enables hierarchical feature learning. Others prioritize width over depth, using few wide layers. The hypothesis is that width provides more expressive power at each level. These choices reflect different beliefs about what makes models powerful. Deep models can learn hierarchical features, low-level patterns in early layers, high-level abstractions in later layers. Wide models can represent more diverse features at each level, potentially capturing parallel streams of reasoning. The right balance depends on the task, the data, and the compute budget. Another architectural trade-off is between dense and sparse models. Dense transformers apply every parameter to every token, ensuring uniform capacity. Sparse models, such as mixture of experts, activate only a subset of parameters per token, allowing much larger total capacity within the same compute budget. Sparsity introduces complexity in routing and load balancing. Which expert should handle which token? But it enables scaling to trillions of parameters. Some of the largest models today use sparsity to achieve capacities that would be impossible with dense architectures. The paired lecture focuses on dense models, but understanding their trade-offs prepares you to understand sparse models later. Stability is another dimension of architectural trade-offs. Some design choices improve capacity but introduce training instability. For example, very deep models can suffer from gradient explosion or vanishing gradients, even with residual connections. Techniques like pre-layer normalization, careful initialization, and gradient clipping mitigate these issues. Some models use additional techniques like learning rate warm-up, where the learning rate starts small and gradually increases, giving the model time to stabilize before aggressive updates. The paired lecture will discuss how modern models ensure stable training, and your task is to understand why stability matters. Unstable training can lead to divergence, where the loss shoots to infinity, or stagnation, where the loss stops decreasing, and what techniques achieve it. Generalization is the ultimate goal.
Models should perform well not just on training data, but on new data. Architectural choices affect generalization in subtle ways. Overly large models can memorize training data without learning general patterns, a phenomenon called overfitting. Overly small models can't capture the complexity of the data, underfitting. The right size depends on the amount of training data and the diversity of the task. Scaling laws, which describe how performance improves with model size and data size, guide these decisions.
They suggest that larger models require more data to avoid overfitting, but also that larger models make better use of data, learning more efficiently from each example. As you listen to the paired lecture, think about the trade-offs behind every number. When a model's embedding dimension is mentioned, ask, why that value? What would change if it were larger or smaller? When the number of heads is specified, ask, what patterns does each head learn, and how does the head dimension constrain that learning? When the feed-forward dimension is given, ask, what's the expansion factor, and why was it chosen? The paired lecture will provide empirical observations and design patterns. This understanding provides the framework for evaluating them. Architecture design is both art and science. Science provides principles. Residual connections stabilize gradients. Attention enables long-range dependencies. Larger models have more capacity. Art provides intuition. Which dimensions to scale? When to prioritize depth over width? How to balance capacity against cost? The best practitioners combine both, using scientific understanding to guide decisions and intuition to navigate the vast design space. The paired lecture will give you the science, the math, the formulas, the empirical patterns. This lecture has given you the art, the mental models, the trade-offs, the questions to ask. In summary, we've explained why position encoding matters, how rope encodes position through rotation, what model shape dimensions determine, and why choices about depth, width, and heads involve trade-offs between capacity, cost, and stability. The next lecture will give you the specifics, the mathematics of rope, the empirical patterns and model shapes, and the design principles that guide modern transformers. Listen for how each choice reflects a trade-off, and you'll come away not just with knowledge of specific architectures, but with intuition for how to design and evaluate them.